Okay, so we've looked at horizontal circles. Now let's look at vertical circles. Vertical circles are a little bit different to deal with because things are changing as you go up and down here. When we had the flat circles, for example, the car going around the corner, the normal force and gravity remained constant, and that was useful for a bunch of reasons. Now, they aren't going to remain. Well, a force of gravity will remain constant, absolutely, but the normal force won't, because of how things are going on here. So let's take a look at what's going on. We've got, in this particular example, we've got a person riding on a Ferris wheel. They're sitting on a scale on the seat. The scale measures normal force. As at the bottom of the Ferris wheel, what does the scale read? So at the bottom of the Ferris wheel, if we keep in mind what we've got here, we've got force of gravity downwards on this person. Everywhere around the circle, we're going to have the force of gravity downwards on this person. They're on Earth. It's going to remain the same. But what's actually happening here? So we know Fg is downwards everywhere. What's happening to Fn? Example 2 is similar, so I'm just going to kind of all do it on this question and on this example and deal with all of the parts of the discussion here. So downwards you've got Fg, but we know this person's operating in circular motion. So there has to be some net force, some larger force acting inwards. So we've got this Fn pushing you towards the middle. Acceleration here is remaining constant. We've got Fg out. So we know because that you are being pushed in, Fn has to be greater than Fg at this point. Fg is pulling you down. Fn is pushing you back up into the circle. At the top of the circle, well, what's happening? You're going to have Fn upwards because you're sitting on that circle. Sorry. You're sitting on that seat as it moves around this circle. But you've got an inward net force. You're traveling the path of the circle. So up here at the top, Fn is actually going to have to be less than Fg. Well, then what happens here at the sides? There has to be some other force acting to pull you in to the middle. In this case, it's probably the back of the seat. In this case, it's probably the seat belt. But either way, at this point, you've got Fg pulling you down. You've got Fn pushing you up so that you remain in the seat. But there's these separate forces pulling you in. So here on the sides, Fn and Fg are actually going to be equal to each other. And it's for these reasons that you actually feel lighter at the top and heavier at the bottom. You aren't, your mass hasn't changed, but you feel an increased normal force at the bottom to keep you in this path, and you feel a decreased normal force up here at the top. Fg hasn't changed, but because the bottom of the seat is pushing on you greater or less up here, your experience of your weight actually changes, which is pretty cool. So let's take a look at example 3 here. It's another Ferris wheel. It's similar to a Ferris wheel. A Ferris wheel is a rigid wheel. The top and bottom of the wheel always have the exact same speed, and the circular motion is uniform. That's not always true for vertical circles. So if you consider a pendulum, so like something, there's a rope here in the middle, a pendulum is going to move faster at the bottom than it is at the top of the path. It's just the way these things are going to work. I don't know if you've ever seen someone on a swing and go all the way around. They're generally going quicker at the bottom than they are at the top of the path. So we're going to split these up here. We'll look at the top and we'll look at the bottom, and we want to write the force equations for this kind of pendulum. You could think of this as a swing. You're going around the bar in the middle, at the top and at the bottom. So at the top, what's happening here? you've got a couple forces acting. You've got Fg downwards. You've also got tension, because this is a pendulum, you've also got tension pulling you into the middle. So at the top, when we write out our net force equation, so F net C equals MAC, and I'm just going to write it here because we're going to need it here in a sec, AC equals V squared over R. We've got two inward forces, and so the net centripetal force has to be T plus Fg. And that's going to equal mv squared over R. Conversely, at the bottom, we've got Fg down, and we've got a tension acting upwards. So again, inwards for a circular motion is always positive. So if I've got F net C equals MAC, we're going to have, in this case, T minus Fg equals mv squared over R. And these are the equations that we've got at different points in the circle, depending on what kind of object we have. So for a Ferris wheel, we've got normal forces, we've got gravity. Here, for a pendulum kind of question, we've got tensions and Fg. Depending on what's actually going on in the problem, you'll have to identify different forces. I'll flip the page. We're going to do a couple more examples, and then we're done. It's a short lesson. Let's take a look at another kind of problem. You have a 70 kilogram passenger moving at 10 meters per second at the top of an upside down roller coaster. So I'm hoping you guys have experienced this. It's a lot of fun. You're inside a loop, so you're upside down inside a roller coaster loop, and we want to find out what force the seat exerts on the person. And so what we've got to do here is we've got to draw our free body diagram. We know that gravity is acting on our person straight down, and we know this person's sitting on a seat. So we're going to have Fn here. Then that's it. There's no other forces acting on this person. So we've got F net centripetal equals MAC, and so we can fill this thing in. The net inward forces are Fn plus Fg. They're both acting in. And that's going to equal mv squared over R. And I should always write it down just so we don't forget. So we can keep filling the rest of this in. We know this person is 70 kilograms moving at 10 meters per second. So we've got Fn plus Fg is just mg. I'll take that middle step here. mv squared over R. So Fn plus 70 times 9.8 equals 70 times 10 squared, and the radius is 8 meters. If you solve this for Fn, you're going to see that the normal force on the seat is 189 newtons. So what does that actually mean in terms of what the person is experiencing? So if you look here at example 5, in the previous question, what would happen to Fn? Assuming this is a scale reading, if the roller coaster is moving faster or slower. Pause that for a second. Let's take a look first of all what this actually means. So Fg is 70 times 9.8. 70 times 9.8. So this person has an Fn on the ground, not moving, of 686 newtons. So at 10 meters per second, the Fn has dropped from what they would experience their normal force being, 686 newtons, or that's their weight, down to 189 newtons. They're feeling increasingly more weightless. What happens if the roller coaster moves slower or faster? Well, that's going to change this value right here. So we can take a look here at example 5 just by adjusting these numbers here. What happens if it's moving slower? Well, if he's moving slower, Fn, then let's pick a slower value and see what happens. Let's say he's moving 5 meters per second. We're going to have 70 times 5 squared divided by 8 minus 70 times 9.8. And let's say he's moving faster. Let's make this thing 15 meters per second. Fn equals 70 times 15 squared over 8 minus 70 times 9.8. What's actually going on here? We can see that this is going to be much larger. This is 686. So do I even actually have to do the math? Well, we don't, but let's. 70 times 15 squared divided by 8 minus 686. This person's going to feel a normal force of 1,282.75 newtons. They're going to feel much heavier. Here, they're going to feel, well, much lighter. If you actually follow this, at 5 meters per second, I get a normal force of negative 467.25. Well, what does that actually mean? Is that possible? At the top, inwards is, or let's talk about it this way. For a circle, inwards is positive, outwards is negative. So this means I have a normal force outwards. I can't. So what this means is if this thing is moving too slowly, Fn is going to drop to 0. What happens if Fn drops to 0? Dude falls out of the chair. So there's a lot of really interesting physics going on in a roller coaster like this. Where ultimately your goal is to find that sweet spot where you can get the person almost weightless here, but not quite. Almost weightless means they're still in their chair, but you get that feeling of falling, which is, well, what roller coasters are going for. Let's do one more example, and then you guys can work on some questions. Let's take a look at that pendulum again. If the pendulum from example 3 or the upside down roller coaster from example 5 are moving at a minimum safe speed, what does that imply? So that kind of takes this conversation that I've been trying to have a little bit further forward. That minimum safe speed implies, in this case, that Fn is approaching 0, or in this case of the pendulum, tension is approaching 0. And so the way that we'd deal with this question is we'd assume, okay, what is the minimum safe speed? Well, the minimum safe speed is what is it just as Fn is approaching 0, or what is it just as t is approaching 0? So that we're still, the person can still make their way around the loop, or the bucket on the string can still make its way, or the pendulum can still make its way around. That's what they mean by minimum safe speed. So what that looks like mathematically is that the tension is going to become 0 and the Fn is going to become 0 in these two cases. So we're going to have mg equals mv squared over r, and we're going to have mg equals mv squared over r. The mg is the inward force of gravity. Because now I've only got one term on each side, they both have a mass, they're going to cancel out, and I'm going to get that g equals v squared over r on both of these things. And so I'm actually going to solve these things for the velocity. You can see I can multiply my r's up and I square root. We're going to get that the velocity is actually equal to the square root of g times r. And what that tells us is something interesting. Again, I think all of this is interesting, but what this means is that the minimum safe speed is mass independent. It doesn't matter what you weigh, you can still ride the roller coaster. You just have to be tall enough so that the belt's attached to you properly, but it doesn't matter what your mass is. That's why there are no mass restrictions for something like a roller coaster. I think that's quite an interesting result. So you're going to take a look at some of these vertical circle type problems. Here are your exercises that I want you to do. Are questions 1 and 2. I want you to do 4. It's not vertical, it's horizontal, but that's okay. More practice. 6 and 7. As always, feel free to fire me an email with questions or show up to my office hours.